So I think that's working.
Venn diagram.
That one. Have a good look.
You sound good.
Social aptitude.
The hands up if you're on that.
Oh, yeah.
Oh,
yeah.
That's a good thing. We have to wear our whatever it is proudly. So double stars are commonly found aesthetically pleasing, and there's an infinite variety of color, separation. They're scientifically and historically important, and can be viewed under any conditions of light pollution, full moon, doesn't matter. Now, this picture is a fairly familiar area of the sky that I grabbed. I got this from Sky Safari, and it shows stars down to 10th magnitude. So every star in this picture could easily be seen in a 3-inch scope. And this is the same area of the sky with many, but not all, of the double stars indicated, just in that one area. They're all indicated by their separations. This is how Sky Safari handles it. It's not a particularly good way to operate, but it shows the sheer number of them.
have you looked at each one of those?
Oh, no. No, I have not. No, you have to have a plan. I'll talk about that later in the talk. You can't just, I don't think you should go randomly at it. Work from an observing list, I think, is the best idea. Now, one of the best known double stars, and probably most everybody, even if they don't call themselves a double star observer, will have looked at Albireo,
Yay.
which I guess now is in the western sky, right at dark, and it's still readily visible. If you get it magnified 50 or 60 times, you'll see a golden star and a blue star in pretty close proximity. If you have good binoculars and you hold them steady, hold them up against a building or a tree or a post, you'd probably be able to see the two stars even in binoculars. Now, interestingly, Albireo is not a real double star. It's an optical one. The gold star is, I think, off the top of my head, maybe 20 light years closer to us than the blue one is. They're a chance line of sight, but that doesn't ruin the effect at all. It's aesthetically pleasing and proves beyond a shadow of a doubt star colors. The colors are real, and they're the result of different spectral types of the stars and their temperatures. And a bunch of lots of double stars have contrasting colors. There will be a list at the end of the talk and some examples, so hang in there. Another double star that's more this season is Rigel, and it's a little bit different than the others in that there's a 6 magnitude difference between the A and the B components. So the B component is almost lost in the glare, but it's certainly visible. A little tiny pinprick beside Rigel. This is another one that is viewable. This is a summer one. It's in Ophiuchus. It's 70 Ophiuchi is one of the first to be discovered to be actually physically bound binary, where the two stars are orbiting around their common center of gravity. They take about, I think it's 70 years. So they've done 3 or 4 orbits since, or two orbits since discovery in the early 1800s, which means the orbit is really well known. By the way, those who own Newtonian telescopes will recognize the diffraction spikes and know the reason for them. It is because of your secondary mirror, thus the support vanes for it. Double stars exist in popular culture as well. So I'm just gonna have a sip. Oops. Is everybody still there? I hope you are. I
Yeah.
can't hear any. Getting no feedback.
Hey, Dave, I have a question. You like
Yeah, go ahead.
Halloween? Have you read the story Nightfall?
Yes, I have. Is that Clark or Asimov? I forget which. Asimov. And it's about culture that's in a multiple star system, but that's inside a globular cluster. So when they finally get nighttime, they all go crazy looking at all the stars. It's a wonderful story. Okay, so now we have Castor, is a nice bright double star to start out on in the when you're first looking for other double stars other than Alberio and Mizar, which what everybody looks at. It was discovered in 1678 to be double, so it hasn't even done one rotation yet. Its period is 450 years.
Oh,
So it hasn't even done one rotation yet, but it's done 3/4 of one probably, and so they know the orbit really well. This photograph is interesting because it's one of the few photographs that showed diffraction rings. This shows what the actual stars look like under high magnification in a telescope. There's a central dot called the spurious disk or the central disk, and it's surrounded by one or more rings, the diffraction rings. And this is a result of physics of light going through a circular aperture. It does this. The stars themselves are actually only points, no matter how they're points. They cannot be resolved in any ordinary telescope. So, but these diffraction artifacts actually have some dimensions. They're particularly measurable, I guess, or observable. Which brings us to astrophysics. As I said earlier, the double stars are astrophysically important. In fact, they and early astrophysics went hand in hand. When the first stars to be discovered to be double, when they first had telescopes in the early 1600s, and they saw these doubles, the first thing the scientists or the observers thought at the time was that these were stars that were just chance alignments, and that the one star, the brighter star, was closer and the fainter star was distant. They had no idea that stars had different intrinsic intensities of their own. So they were observed closely because they thought maybe parallax would happen. So they knew that the positions of the stars would move back and forth relative to every 6 months when Earth was on the other side of its orbit. And they thought that's what they would see. So they measured very, very carefully. And to their surprise, they found that many of these things were not doing that, but instead the one star was following a curved path around the other star. And Keplerian physics became a thing right around then. It became determined that the orbit of, now this gets complicated. I'll say what we mostly think is the one star, the smaller star, orbits in an ellipse around the brighter star. But that's not correct. They both orbit in an ellipse around their mutual center of gravity. But for the sake of the math, and it doesn't make any difference, or for the measurement, they picture the brighter star as being fixed, and the other star going around in an ellipse around it. So one star, you see where it says F1 near the bottom, that's one of the stars. It sits at the focus of the ellipse, and the other focus, there's nothing there. And then the orbiting star follows that elliptical path. And Kepler got to tell us that the areas shown in green in this diagram are equal. for something traveling an elliptical path, which means the distance from the primary, or distance from F1, the companion star slows down. And when it's near the primary, as you see between T3 and T4, it speeds up. This is also true. The more complicated scenario of the two orbits around the common center of gravity, it still follows that. But the simplification of pretending one star is fixed works, and that's how they've been measuring these things for years. And when you got Kepler laws and Newtonian laws of gravitation, they could find out the mass of the stars, which was huge to find out that the stars had different masses. And this was the infancy of astrophysics as we know it. Start to add the work of Hertzsprung and with the colors, spectral types, and so on. And double star observers and observing was at the forefront of astrophysics from the 1700s right up, even until now to a certain extent, but not quite as much now. Here's Castor's orbit. Now, there's a few things to point out here if we're going to talk about physics. You notice that Castor A, the yellow dot in the middle, is not at one of the foci of the ellipse shown. The ellipse shown is the actual elliptical orbit of the other star, but tilted on the sky. It's not face on to us. It's tilted. So Castor A is at the focus of the real ellipse, but it's not at the focus of this projected one. But no matter, the orbit of the that you see, the tilted orbit, still follows Kepler's laws, amazingly enough. I don't know enough about math to prove that. I've just been told it. So if you look at a period of time, look at the position 1970 and then 2000, and make a little triangle out of those two and Castor A, you'll see a certain area. Then look at across the other side between 2200 and 2300. It's a much larger area. Sorry, what I meant to do was between 1970 and 2000, and then between 2000 and 2050. The thing is that the B component is slowing down as it goes around. Its actual physical speed through space is slowing down. And the place where Castor B is closest to A is around between 1970 and 2000, and it's that's where it's moving the quickest. See, it's covering about, I don't know, 80 degrees of angle in about 30 years, whereas between 2200 and 2300, it's also covering about 80 degrees of angle, but now it's in 100 years. So that's the slowing down. Another example, this is a little bit better. Gamma Virginis, also known as Porrima, is a double star in Virgo. And here is its orbit. And interestingly enough, its orbit, this is the real seen on the sky orbit, is virtually identical to the actual real orbit. In other words, that ellipse that the B star makes around the A star is pretty much perpendicular to our line of sight. So we're seeing the real ellipse there, pretty much. And you'll notice that one end, where it's in close to the star, 2000, 2002, 4, 5, 6, it's moving a considerable angular distance every year. But now go out to where it says 2025 or close to it, and you see it's slowed down. So that's the actual orbit. You could actually, if you took photographs judiciously at 2002, 4, 5, 6, 7, 8, with a big telescope, you would have a document of the actual movement of the star. Stay tuned. I have something like that coming up. All right. Now, generally speaking, there are three things we look at in a double star. The distance between the A component and the B component is called separation, commonly measured in arc seconds. And then there's the angle formed between north and the line joining the two stars. And it's that's called the position angle, or PA. And the third thing that they measure, of course, is the magnitude, brightness of the stars. They also measure the spectral type and so on, if they can. Yeah. So there's a lot of data collected. But the primary ones for you to know what a thing looks like in your telescope is the magnitudes of the two stars and their separations. 1 arc second, just for reference, is a 1/3600th of a degree. The moon is 1800 arc seconds across. Think about that for a second. 1 arc second is the size of a quarter seen from a distance of 1.8 kilometers. It's a mind-bogglingly small angle, and these are the angles, and even smaller, that we, in the hobby of double star observing, routinely encounter. Now, it's important to take a quick look at how your telescope forms images. So there's a little bit of optical physics here, but again, it's just a general discussion. It's not really mathematical or rigorous. But a diffraction pattern consists of a number of parts. There's some discussion of what the real names of these are, but there's a central spot of bright light, and then there's a dark ring, and then a light ring, and then a dark ring, and then a light ring, and so on. And these tend to go out theoretically to infinity, but for most stars, you only see 1 ring, sometimes 2, if the star is a little brighter, except for stars like Sirius, where you may see 8 or 10 of the rings. And it gets to be quite a mess to look at. The center of this pattern is the actual location of the star. And then we have the central disk. And the central disk varies in size by the magnitude of the star. So in a fainter star, that central disk won't be as big. But the airy disk, which is from the first minimum in the pattern, I wish I could put a pointer on this, and I can't. I really wish I can't. And this presentation thing doesn't allow that. The distance from the center to the first minimum defines the edge of the airy disk. And then the rings. Now, these are the central disk contains 84% of the light of the star. The remaining 16% of the light of the star is spread out amongst the rings, and most of that's in the first ring. You can see the second ring's dimmer, third ring's dimmer again, and so on. It's for all you math wizards, it's a Fourier series, which that's all I'm going to say about that. And here's the thing about why I'm talking about this. The aperture of your telescope has a lot to do with the resolving power and how large the pattern is. So these diagrams represent from a 60 millimeter scope to a 200 millimeter scope at the same magnification. That's important. At the same magnification, you will see that the whole pattern shrinks as you get more aperture. And if you think of these as pixels, when the pixels are big, like for a 60 millimeter, then the picture is blurry. And if the pixels are small, like a 200 millimeter, the picture is sharper. Planetary imagers certainly know about this. Well, this is also true if you picture that if two of these diffraction patterns are very, very close together, then the two diffraction patterns are going to touch or overlap. And so you get a situation like this where the two central disks are sort of kissing or touching each other. And this is when you pour on the magnification of a close pair in your telescope, this is often what you're presented with. I'm going to back up here. Double star. Sorry about the pause here. Oh, sorry, I'm on this picture here. This could be what a pair of stars that are 1.5 arc seconds apart looks like at 200 power in a 100 millimeter scope. It also is what a pair of stars that are only 1/2 arc second apart look like in a 200 millimeter scope. If you have questions, yell, because I'm not sure I'm nailing all this perfectly as an explanation, but it has to do with the varying size of these disks. If you have two of the 200 millimeter diffraction patterns, then you can have the stars can be seen as two stars when they're a lot closer together than the 60 millimeter one. I have other pictures that might help here. Here's another really close pair. And here we go. Maybe we'll do it as graphs. So this is now a cross-section graph, a series of them, across a diffraction pattern. Look in the middle first at diagram E. That's a single star. The vertical axis is the intensity of light. And so you have the central bulge, which is the central disk, and then you have the rings. And the peaks of the rings go on outward like ripples on a pond. They keep going. And for those into calculus, the area under the curve is the amount of light in each, in terms of photon flux. But see what happens now in diagram A, you put two diffraction patterns really close together. In situation A, the two disks will clearly be seen as separate. There'll be black sky in between. In B, now they're starting to get to the point where they're touching. And C, they're kind of maybe overlapping. And in D, the two stars are so close together, they just make one diffraction pattern. Here it is, looking at it another way. So I'll just back up here. Where it says split on the right, that's diagram A. Where it says resolved or notched, that's diagram B. Where it says elongated or unresolved, that's diagram C. And the last one is unresolved. It looks no different than a single star does.
David, I have a question.
Go ahead.
Do you prefer a slightly smaller aperture telescope without a central obstruction, or a larger telescope, let's say 2 to 3 inches separate the two telescopes, that may have a central obstruction for this type of work?
In terms of central obstruction, and I have a slide in the talk about this a little later on, the distance or the difference between having and not having one for double star observation is minimal. And at the close, at the small angles we're talking about, the seeing of the atmosphere is more of a player. All of these diagrams and pictures are well and good, but we haven't put them through Earth's atmosphere yet. So I discount the difference that a central obstruction makes in double star observing, and even to a certain extent in planetary observing as well. I'd be happy to chat about that at some other time. There are two important limits or rules of thumb, or whatever you want to call them, that people use in the hobby of double star observing. Dawes limit is an artificial limit created by a man, strangely enough, by the name of Dawes in England in the 19th century, where he observed as many pairs as he could that were equal in magnitude. And he did it with as many different telescopes as he could get his hands on. And he came up with a rule that in order to see the two disks as distinct, they would have, I don't know what that was, they would have to be separated by 4.56 divided by d arc seconds. So for instance, if you just did 4.5 and your scope was a 3-inch, you could, that would 4.5 over 3.0 would be 1.5 arc seconds. So the Dawes limit for a 3-inch telescope would be 1.5 arc seconds, and so on. There it is also in metric. Now, but that's a completely arbitrary limit. It doesn't have anything to do with physics. But then Lord Rayleigh came along, who was the Astronomer Royal, not long after Dawes was around, and he said, well, an actual limit that we can actually quantify in physics is the Rayleigh limit, which is slightly larger because it's the distance between the two airy disks where the maximum of one disk is placed over the minimum of the other. In other words, it's the width of the, I'm going to go back here, ding, 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 ding. The airy disk. See where the red lines are? The width of that is the Rayleigh criterion, the Rayleigh rule, whatever. And it's 5.45 divided by aperture in inches. Interestingly, the picture on the right here that says split, that's what a Rayleigh criterion split looks like. And the one that says resolve, that's a Dawes. So Dawes, you get basically a snowman or a figure of 8. Here it is diagrammatically speaking. On the left, we have the Rayleigh. And you can see that there's a minimum between the two disks that is discernible as a black line or a gray line between the two disks. Whereas with Dawes, there isn't really a gray line between, they're more merged. Here's another way of looking at it. The Rayleigh split is well resolved. The Dawes split is just resolved, and not resolved means get a bigger telescope. That's the only way you're going to do it. You can pour all the magnification you want at these things, and the physics does not change at all. So generally speaking, here's a chart, and you can find this in any book, or you can look up the Dawes and Rayleigh limits for your particular telescope at any time. But notice, even for a 60 millimeter scope, we're getting in around 2 arc seconds. So that's 2 quarters side by side. That's at a distance of 1 kilometer. That's a really, really tiny angle. And you can see that with a 60 millimeter scope. And you know, the increases as you go up in aperture to, well, I've gone as far as 10" with this chart. Now you're into half an arc second. There's a fun place we go to. We double as star observers. We call it subarc second land. And that's sort of the holy grail. We're trying to split optically with our eyepieces and our telescopes pairs that are less than an arc second. It's fun to do. Now this is about obstruction, and the diagrams aren't great. But the effect of obstruction, so I have an unobstructed 6" refractor and a 1.5 second arc pair. So a good black sky in between. And then a 6" with a 25% central obstruction. These were generated by a guy named Damien Peach, who's a well-known planetary observer, but he has lots of good stuff on his website about resolution and the effect of airy disks and obstructions and all that kind of stuff. But you can see in the second diagram, maybe you can see that the central disks are ever so slightly smaller, but you can see the rings more clearly. What the central obstruction does is it takes some of the light from the central disk and puts it into the rings. So the rings become a little brighter, but the central disk becomes a little smaller. So theoretically, with an obstructive scope of 25%, you could slightly, very slightly, whoops, I'm talking second decimal place here, improve upon these numbers that you see in this chart with an obstructed scope. It actually slightly improves the double star splitting ability. Now, everything I've said up to now about all these patterns and the airy disk and the Dawes and the Rayleigh have shown equal pairs, stars that are the same, two stars close together that are the same magnitude. Well, on millimeters, and the vertical axis is the difference in magnitude between the two pairs, between the pair of stars. So for instance, you see this one Eta Geminorum. So it's the second one in the upper left. It's and the two lines for the Dawes limit and the Rayleigh limit are there. It's clearly within the range of being splittable with a 4" except for the fact that the difference in magnitude between the stars is nearly 3. So the bright star overwhelms the smaller star, and you actually can't see it as double. So really the lesson from this is if the stars are equal, the Dawes and Rayleigh limits work. But there are very, very, very few pairs in the sky where the stars are precisely equal. So you're somewhere else and you're in the blue zone or the gray zone or the white zone, depending on magnitude difference. Now, I said this about seeing before. All of what I've just said in terms of actual actual under the sky viewing changes because we have to look through our own atmosphere. So at the top of this picture, there's a nice flat wave front coming at us from outer space. And the first thing it does, it goes through some turbulent air. And then there's wind shear. And it causes the atmosphere to act a little bit like zillions and billions of little lenses. So if you look at the third, it says wave front distorted by turbulence. You see, it's a bunch of line segments joined. Each line segment is a kind of lens, and it produces an airy disk, a diffraction pattern. But the trouble is, because of the seeing, the airy disk gets moved around. It's not in its actual location. It's a little bit off. And look at diagram 1. That's the so-called speckle image. And each one of the bright spots in that is a separate airy disk of the actual star. And they're distorted and not good in the, it's quite a mess. But I think we've all looked through our telescopes and see stars that look exactly like that on some nights when the seeing is bad. And then, but if the seeing gets better and the air is steadier, you start to go through Pickering's scale, and starting at about number 3 or 4, you can actually see the diffraction pattern as an entity, although it may be moving and jumping around. If you're lucky enough to get to 8, 9, or 10, that's Nirvana night, and you should stay up all night and use all your eyepieces and Barlows and observe at 1,000 power, because you won't get to do it very often. By the way, the Winter Star Party, which I will be attending this year, features some of the best seeing in North America, because it's basically you're on an island out in the ocean, in the Keys there, and the airflow is very, very non-turbulent for the most part. So you get a lot of from about 6 to 10 there, where if you're in the typical, Great Lakes Basin, East Coast, doesn't really matter. You're more often going to be going from anywhere from 1 to 6. You'll think 6 is a real good night. The other thing about this is that, and this has to do with where they say that a smaller telescope will give a more pleasing view of Jupiter than a larger scope if the seeing isn't good. And that's because the larger scope is trying to put together an image of Jupiter using speckles that are like 1, 2, and 3. Well, that just blurs everything out. On the same night, a smaller scope will see that same part of sky at like 5 or 6 or 7. It won't reveal as much detail, but the detail you do see is easier to see. I could do a whole talk just on that, but I won't. So that's kind of the technical side of the I'll pause here if there are any questions about the sort of the what I've done so far. How am I doing here? Are you all there?
Yeah.
So,
Oh, okay.
I know that you say you weren't going to do a talk about smaller scope versus larger scope. But on night, so do you have a night where you have average seeing? At what point do you switch from the larger scope to the smaller one?
That's a good question, and there are pages and pages of debate on that on cloudy nights. Because seeing is not static. Seeing is a very, very ephemeral thing, and you can have moments of terrific number, Pickering 10 seeing popping up when it's ordinarily Pickering 5. The stars jitter around and jump around, but there are moments of good seeing. Any experienced planetary observer trying to see detail on Jupiter will tell you, if just keep looking, it'll get better for a minute or two, or a few seconds. And that's the thing. If you switch to the smaller scope because the seeing is mediocre, you may miss an opportunity that your larger scope could have brought you. So I don't know if there's no definitive answer to it. How many people would spend an hour at the eyepiece just looking at Jupiter, or 2 hours just to make one sketch? I mean, in 2 hours, the whole thing, it rotates a fifth of the way around, but that aside, you know, it takes great patience to tease out of mediocre seeing those moments of good seeing. But if you don't use your larger scope, you're never going to see them. Does that answer your question? Hello.
Sleeping,
We're
we're
here.
here.
Sorry, it's the sound is cutting off or something, and or there's a threshold of below which the sound from your room, the room you're in, is not being broadcast to me. So I'm kind of just talking at my computer screen and hoping that everything's still working. Excuse me. Oh, I need to have another medicine. Okay, any other top questions about the technical aspects of things before we get into the aesthetic?
What's the pretty stuff?
Sorry?
What's the pretty stuff?
You want the pretty stuff. You want the pretty pictures. Okay, well, here we have, I've assembled, and I can say that this is a blend of two talks. A talk I wrote just for this, and then I added in the stuff from the Carl Jorgensen Memorial Lecture from the AAR and added that in. So they're both included here. But you know, you'll be happy to know that everything you've seen up to now, I wrote that for you guys. So,
Thank
yay. Okay, now there's to simply say double star is such an oversimplification. For one thing, there are double stars where you magnify them, you see two stars. There are color contrast double stars where you observe them and you will see that they're two different colors. But there are also triple stars. There are double doubles, which is two pairs near each other, but there are also multiple stars. And another factor is that not all the double stars we look at are actual orbiting pairs. A lot of them are chance line of sight alignments. And I toyed with the idea of going into that and trying to research that for each of the pairs I'm going to show you. And I decided, nope, needless complexity. Let's just look at a few, and I'll throw these at you so that, and there is a list. Apparently it's been published. I made a list of everything with all the RAN deck and the information, which is now apparently has been emailed to all the club members. Is that correct?
Yes, and it's on the website too.
And it's on the website too. Okay. So the data from all the stuff I'm about to show you is in your hands. You can go find it at your leisure. So first we'll look at just sort of ordinary, well, not ordinary. I don't believe any of them are ordinary, but just some double stars to get you started. In triangulum, this is a nice bright pair, 15 triangulum. The beauty of this one is that its separation is 142 arc seconds, which means that easily splittable in binoculars. And you can look at this in relatively low power in a telescope, you know, 30 power, 40 power, 20 power, and still get a nice view of it, and with the surrounding background stars. I always like to picture, even if they're not real pairs, real orbiting pairs, I like to picture them as such, and that they're slowly journeying through space together across this, you know, over thousands of years or whatever. I don't know, that's a mental image I get. It's highly unscientific and totally romanticized, but it's a good way to look at these things. Castor we talked about before. In Gemini, it's the second brightest of the two stars at the head of Gemini, even though it's alpha. I don't know why they did that. And in this picture, you'll notice that there's two bright stars. They're separated about 5 arc seconds. There's a much, much, much fainter star. You can just see it in the upper right there. It's about, I think, 9th or 10th magnitude. It's gravitationally bound. This whole thing is a gravitationally bound system, and each of the three stars is double in and of itself, although not visible in amateur telescopes. Too close. So there's 6 stars in this picture, which is rather remarkable. If we go over to Orion, then we'll get one of these, is it Dawes or is it Rayleigh split, depending on the size of your telescope. With a separation of 1.8 seconds, you're going to be to get this view of it, you're probably 80 millimeter scope or a 90. It's quite bright. It's just above Rigel. It's a bright enough star. So you don't have to worry. You can throw all the magnification you want at double stars. There's no such thing as too much with double stars. Throw at whatever the your mount and the wind will allow. Rigel itself is an interesting double star. And it is of similar type in terms of the viewing experience to Sirius, which I will talk about in a moment. A extremely bright star, magnitude 0.3, quite close to a fainter star, 6.8 magnitude, 9 arc seconds. So the split is not a problem. The problem is putting enough magnification on to get the small star out of the glare of the bright one. This is doable in most scopes, kind of 100 millimeters or more, maybe less. Try it. Don't give up on if you only have an 80 millimeter to do this with. Try it anyway. More of the fun of this is trying stuff and writing down your results, and then giving a presentation at your next club meeting about what you saw and what you actually observed. Now, Sirius is a well-known challenge to see. The picture on the left is Sirius, and that great big blob is just the overexposed image of Sirius, and there's a tiny little blob at about 11 o'clock, just about touching it. That's the other star, 8th magnitude. But look at the magnitude difference, 8, 9, it's 10 magnitude difference, basically. 8.4 minus 1.5, yeah. It's 9.9 magnitude difference. That's huge. And if you remember the diagram that showed the white area and the blue area, this one it's way up. It's hard. It's a very serious observing challenge. But if you have steady seeing, it's doable even down to 100 millimeter scope. Adhara, which is also in Canis Major, is similar. And the trick with Adhara, or with seeing Sirius, is look at Adhara first. In its little companion star, see, they're only 6 magnitudes different. If you can see the companion of Adhara, then you might have a shot at Sirius. The thing is, not where we are, well, you're a little further south than me, but not much. I'm at 44 degrees. What's your latitude there?
40.
40? Oh, well, yeah, that's 4 degrees difference. It's enough to get them a little bit further up from the horizon than what I have here. So that's a factor. But it's worth trying. Again, there's no such thing as failure in this hobby. You can safely say, I observed Sirius last night. I looked at it for half an hour. I didn't see it. I didn't see its companion, but I still observed it for half an hour. That is a success.
Have you ever tried blotting out using an eyepiece and piece of oil or something on one side to blot out the brighter star to try to find a companion?
I've never been that handy to do that to one of my eyepieces. I never wanted to. Basically, all I have is Teleview eyepieces, and I don't want to mess around gluing a little piece of metal to them or whatever to put an obstruction. Some of the eyepieces, in order to get the obscuration, whatever you call it, the occulting bar in focus, you have to take the eyepiece apart and put it in between the lens elements. No, I'm not going to do that. I think a simpler eyepiece might work. What you can do is stick Sirius off the edge of the field of view in the right direction, and the companion may become visible.
That's from 2007? That picture?
Yes, they're wider now. 2007, they were probably only at about 9 or 8 arc seconds. Sirius A and B are about as far apart as they ever get. They have a 50, or is it 80? I can't remember. It's less than 100-year orbit. So it's going to start closing up again. And when it's closed tight, 3 arc seconds, 2 arc seconds, no chance.
Right.
But that'll be 50 years from now. And I don't care. So, all right, let's move on from here. Now, some double stars have very obvious color contrast. The example of Albireo was given earlier. The color contrast is sometimes quite striking. Here is a pair in Camelopardalis, 11 and 12 Camelopardalis. So they each got their own Flamsteed number. And they're a lovely bluish white and orange. And they're 178 arc seconds apart. So again, this is a binocular pair. But what's interesting is you get this picture, you get this into your telescope, and just look just above the orange star. Isn't that a tiny little triple star there? At about 1130 from the orange star? I think I see one. Once you start exploring around, you might see some other stuff that's better to look at than what you started looking at. Improvisatory, but yeah, the color contrast is there. It strictly has to do with spectral type. So the blue one here is probably an A or an O or a B, probably a B star. B. It's either an O or a B, and the other one is probably a K or an M. Alpha Hercules. This one for the summertime, nice and bright. And the color contrast in this one is a little more, it's like 2 different shades of orange. Pale orange and not quite as pale orange. The colors are always subtle. And what's interesting is they are, to a certain extent, occurring in your brain, that your eye perceives color contrast that may not be there. That's hard. No, that's poorly stated. The eye, like if you were to look at either one of those individually, well, let's go back. If you were to look at either one of those individually, you probably wouldn't particularly note the color. You might see that the orange one was a wee bit orangey yellow, but put a bluish one beside it, and your brain has something to work with. And then it realizes, that, oh yeah, there is color contrast here. The colors for the most part are fleeting, but well worth the search. If anybody's looked at carbon stars, we have a carbon star on the list a little later here. 20 Geminorum. I don't know if this one's color, but it's just a nice bright one, and it's roughly equal pair. Separation 19 arc 20 arc seconds, so pretty easy, maybe even splittable in binoculars. This is I can't read the screen sharing bar is in front of the top there. What's that say?
3925.
Oh, yes, H. So this is a John Herschel discovery in Canis Major, and it's known as the Winter Albireo. It's a similar separation to Albireo. It's a little bit less at 26. The magnitudes are roughly equal, and it's very definitely an orange star and a blue star. It's absolutely gorgeous, and it's probably other than Albireo itself, it's probably the best color contrast star in the whole sky. And it's a little bit south and east of Sirius, so not at all hard to find. Again, there's the RAN deck of all the different stars is given in the chart table that you have. So this is well worth looking for. And again, look at it at the lowest power that you can see that actually splits it. And then you get to see the background. You get to see it in the context of all the other stars that are there. And if you look at this picture, there's just pairs of stars everywhere. Are they all double stars? Don't know. You'd have to look at the movements of each of them. I mean, just at about 10 o'clock to the left of up, there's a little blue pair there, tight little, tiny little blue pair. And there's another one with, are they actual double stars? I don't know. I don't know if they're in catalogs or not, but they're everywhere. Our brain picks out patterns, don't forget. We are pattern, we find patterns. This is Delta Cephei, an important star for an entirely different reason, but it's a lovely colored double star of pale yellow and blue. And the yellow star is a Cepheid, is the original Cepheid variable star, the first one discovered and described and had science done on it. It varies in magnitude over a very precise, I think, 5-something day period. So it would be interesting to maybe image that. Here's a project, image it every night throughout its cycle at the same exposure and see the difference. That would be interesting. There's quite a lovely looking triple star just to the right there, isn't it? If you could see it. These pictures, some of these pictures, I got them from the internet. Some of them are from very, very large telescopes indeed. And most of those background stars actually wouldn't be visible in your telescope. Waiting till spring, you can get this one. This star is also known as Izar, I-Z-A-R, no M. And it's a very tight little colored pair. Rather challenging in a lot of different scopes because of the magnitude difference, which is 2.6 magnitude difference, and also because of the closeness. In some telescopes, depending on the size, the little blue star sits right on the first diffraction ring of the brighter orange star and makes it really hard to see. But again, your mileage may vary. Here's the one with the carbon star. Now this is, I can tell you for a fact, this is not a related, gravitationally related pair in any way, shape or form, but WZ Cassiopeia is a carbon star, and it's one of the reddest stars in the entire sky. It's in the top 10 or 15 of the reddest stars in the sky. And it's beside an otherwise unremarkable bluish white star, but to see the two of them together is quite a thing. And they're quite wide, binocular, visible easily. Yeah, I don't know what else to say about that. Okay. Now we have triple stars. The first example is Iota Cassiopeia. And so in very, very tight surroundings, the A star is the bright one in the middle. 3 seconds away is the B star. And 7 seconds away is the C star in the other direction. So they're an extremely tight little group. And the range in magnitude from 4.7 to 9.1 makes it, you're probably going to need 100 or 120 millimeters to really see this effectively. There's no colors in, I think the colors are accurate in this, in that they're just white stars. But fascinating to see that many relatively bright stars in such a small space. This 2816, I should explain what an STF is. STF is the code in the Washington Double Star Catalog for Friedrich Georg Wilhelm Struve, just known as Wilhelm Struve, who was the great discoverer of double stars in the late 18th and early 19th century. He discovered and measured and cataloged over 3,300 pairs of stars over a 30-year career. A remarkable person. And so you'll see this. Sometimes the STF is given as his name, Struve 2816, and sometimes it's given in some atlases with the Greek capital letter sigma. So you'll see something in an atlas or a chart that says sigma 2816. Well, that's this one. And again, this one's really, really nice for any scope, being as bright as it is, and the separation is generous. And I do recall that the central star, the brighter one, is golden a bit compared to the other two. Well worth looking for. This is in Auriga, so it's in the winter sky. No, is it Cepheus? Cepheus, sorry. Cepheus? Cepheus. In Lynx, a constellation that most of us with a star map and both hands couldn't find in the sky. It's a very unremarkable constellation, along with my other favorite unremarkable constellations, Camelopardalis and Equuleus. If you can find those, you really know your stuff. This is a lovely little one, but the brighter pair, again, this shows the overlapping diffraction patterns. At 1.9 arc seconds, you're going to need probably 90 millimeters or 100 millimeters to see this effectively. There's no color contrast in that, but you know, some reasonably bright stars, all again in a very tiny little space in the sky. Now, this one's of particular interest to me. I have a long-term project going that I'm in the middle of, but this is Zeta Cancri, and it's a nice triple star. The two that are close together, the brighter of those is A, and the other one is B, and C is the one down below. I think it doesn't really matter. The two close together are orbiting around their own mutual center of gravity, and then those two orbit around the other one. So it's kind of a complex situation, but the beauty of and where I got this project going, the tighter pair orbit in 50 years. They do one complete orbit in 50 years. So elementary math says about there's a 7-degree change in angle in a period of 1 year. And I using the line that joins the bright one and the third star down there at the bottom. I have been on a project, and I'm going to finish the project. Well, maybe I won't finish it yet, but this is what I've got. Zeta. Now I got a picture I took in May of 2014. And what I did was I lined up the A star and the C star vertically on my computer screen. And then I got an image that was taken by a colleague, Steve Smith from Colorado, that was taken in 18. And you can clearly see the angle has changed. And changes from 30-something degrees to 50-something degrees in 4 years. Well, what did I say? 7 degrees a year. So 7 times 4 is 28. So there you go. There it is in real life, actual movement of stars visible and imageable in amateur-sized telescopes.
That's very cool.
Yeah, there aren't very many binaries that you can do this with because they have to be close enough to Earth, bright enough, and separated enough, but not too separated, because when they get widely separated, like the AB pair goes around the C pair in 1,000 years. So you're going to hand that project off to your ancestors, or sorry, your descendants. Your ancestors don't care. So there aren't many stars you can do this with. And again, the slow movement of the AB pair around the C pair means you can sort of use that as a baseline. This isn't really probably true. In 4 years out of 1,000 years, so that's 1/250th. Yeah, that the AB pair relative to C might move something in the neighborhood of a degree a year. No, not right. That would be 300. 1/3 of a degree a year. But you can, because that's so slow moving, the AB cross C pair is so slow moving, you can use that as a baseline to watch the other ones move around. But I'm going to image these again. The imaging process, by the way, is another talk I have. But basically, it's video lucky imaging. It's the same thing planetary guys do, except you just do it with double stars. So long focal lengths, make a movie, find the best frames, stack them. That's what that is. But it is cool. How many, I mean, where else can you see, stellar movement? I suppose you can watch Barnard's star, take a picture of it every 2 years for 20 years, and you'll certainly see that moving, and a few other stars. But in terms of the, there aren't many that you can do this with easily. Another triple stars, 16 and 17 Draconis. 16 is just an individual star, whereas 17 is a double star. So between the two of them, you get a binocular. Well, I shouldn't say binocular. The 17 star, the separation is only 3.1, so you're not going to split that in a binocular. So you're pretty much going to have to hit this with a telescope. The separation between the two stars, between 16 and 17 is 90 arc seconds, but that's binocular, but you're not going to see the third star without a telescope. Now, this is astrophysically and pop culture. First of all, Omicron 2 Eridani is also known as 40 Eridani. That's its Flamsteed number. And all you good Star Trek people will know that the bright star in this image is Vulcan, supposedly. And it's much larger than the other two stars. And so those two little stars, they orbit around each other. It's rather much like the Zeta Cancer one I showed earlier. Those two little stars go around the big one really slowly. But there's more fascination with this because the two little stars, the white one is a bona fide certified white dwarf star. And it is by far the easiest white dwarf star to find and observe with amateur equipment in the entire sky, because it's 9.5 magnitude, and you know where to look for it because it's in this triple star. But what's really more fascinating is that the little red star, it's a red dwarf. So you got a white dwarf orbiting a red dwarf around a main sequence star. It's quite and this again is very close to it. It's only 12 light years away. So it's, that's in our local neighborhood. So have a look at this. This one is, it would be up now. West of and a little bit south of Orion. Get your scope out and pour the power on and have a look at that. You are not going to conveniently see a white dwarf star in any other way. Without, if it's just individual and it's sitting there in a field of stars that are all faint, it's like finding Pluto, except the white dwarf isn't going to move and show itself to you 3 days later. It's just still going to be in the same spot. It'd be very hard to see. So this is your opportunity to see a white dwarf and a red dwarf all at once.
Do they go around each other in a reasonable?
Yes, the little ones go around each other. They have their own Barry center. I'm sure all the physics people know what that is. It's the mutual center of gravity. And then the two go around the big one with another mutual center of gravity. Even with three bodies, it becomes quite a mathematical thing to determine the actual movement of them all. And that's why it's convenient to place one at a fixed point and use the orbit projected on the sky as the actual orbit of what's happening. To try and picture it in reality, I don't know. I was reading about this, and assuming that there were people, Vulcans perhaps, on a planet orbiting around Vulcan, they would see those two little stars as a -8 and a -6 magnitude pair of stars in their night sky. So brighter than Venus, but not nearly as bright as the moon. So it wouldn't wash out their night sky, but they'd be able to see those stars if they were above the horizon from their location. Interesting to contemplate. And arguably one of the most aesthetically pleasing, if and only because of triple stars, because of its, again, the tightness. They're all white stars. It's Beta Monocerotis. Beta Monocerotis, forget it. Beta Mon. Again, because of the tightness of BC, you might want to be getting in an 80 or a 90 millimeter scope. Will show these nicely because they're nice and bright. Just put it up to 150 power. Use your Barlow, and you'll see these pretty much like what you see right there. In a larger telescope, of course, you'll get more separation, more black space between the close pair. Now, everybody's looked at the double-double. You know, when I think of people who aren't really double star observers, but they know about some double stars, what are they going to look at? They're going to look at Albireo. They're going to look at the double-double, Mizar. And then they go on to go look at their faint galaxies from there. But there's lots of double-doubles around because you don't really have to have much for a double-double. You just need two individual double stars close to each other. This is one of the better ones in Lyra, Struve 2470 and 2474 at the top and the bottom of the screen. If you look at these, they're separated by about 10 arc minutes, so a third of the moon. So a low power, 50 power or so eyepiece, maybe even 100 power, will get you both of these in there. And what's really interesting, and I find this, because they're so similar looking, other than color, similar angle, a similar separation, similar brightness, it appears to me that they're flying in formation through the sky. Again, my fanciful aesthetic for these. This is quite a nice one, and it's, you know, if you're looking at the double-double in Lyra, which is only a few degrees away from this one, consider that it's 3 arc minutes apart, but the individual stars are quite a bit closer together. I guess I should have put that one in, but I didn't, because everybody's seen that one. Now, everybody looks at M81. What a lovely galaxy. And everyone pretty much ignores the double-double that's right beside it. In most photographs of M81, you look in any book of a photograph, you'll be able to see Struve 1387 as double in the photograph, just like you see it there at the bottom. Well, the other one's double too. I will just, there's another slide here. I've just zoomed in a little bit. It's still too tight to see in this particular photograph, and I couldn't find any other photographs of it. The closer pair are the brighter stars, 2.2 arc seconds. So again, you're probably 100 millimeters or more aperture, and you'll be able to split that one, and you'll be able to split the other one even more easily because it's wide, 8.9. And it's right beside something everybody looks at all the time anyway. So that's a double-double that most people don't know about. And then there's Z Scorpii, which is actually quintuple. There's 5 stars here. The brighter pair above, the bright yellow one, is actually a pair of stars at 1.1 arc seconds. So this is a large scope. This is 8-inch or bigger. Maybe a 6-inch might get it. So like 150 to 200 millimeters. So there's 2 stars where that bright yellow one is, and there's one above it. And then there's another pair just below. That's easy. So you get 4 stars, and with a bigger scope, you get 5. Fantastic. But wait, there's more. Multiple systems. Let me know if I'm going too long.
No,
All right. Sigma Orionis and its neighboring system, Struve 761. So Sigma Orionis is on the lower left there. It is a quintuple system all by itself. But again, with the AB pair, the brightest one, being far too close to split with amateur telescopes at 0.3 arc seconds. I don't know if it's ever been successfully visually seen in anything smaller than like the 40-inch or the 36-inch at Lick or some place like that. But there's 4 there in a nice, attractive little line. And in the same field of view is Struve 761, which is a nice little triple star. So you've got 7 stars in that little part of the sky. I don't recall this having any color aspects to it. And we're going to finish off with one of the most famous multiple stars in the sky, Theta Orionis, also known as the trapezium. Most small telescopes will show A, B, C, and D. And if the seeing is good and you're probably looking at 150 millimeters aperture, there's an E star and an F star. All those other stars in there, I'm not sure that they're that visible. Nobody much looks out there. The stars inside the trapezium are like 15th magnitude. So the A, B, C, D. For some reason, they named these not A, B, C, D, not by brightness, but from west to east. Go figure. This is a north at the top picture. So the A to E, whoops. Oh, I didn't put that in. From A to E and from C to F is about, they're about 4.5 arc seconds, both of them. Finding E and F is a challenge, and it'll tell you whether the seeing's any good. You can have a perfect 8-inch telescope and look at this on some nights and only see the 4 stars, and the very next night you'll see 6. So it's worth revisiting Theta, the trapezium, and not to mention that the whole thing's inside the Orion Nebula. Okay, home stretch. Now you can look these things up. The Washington Double Star Catalog is the central repository, the Oxford English Dictionary of double stars. It has 155,000 pairs or systems in it. Some of the systems have multiple stars in them. It's in this huge table. It's hard to look up stuff on it. I used to use it until a fellow in Italy came up with something called Stellodopy, which is Italian for double star. And he created a search engine, and this thing is fantastic. You can make your own observing lists. For instance, suppose you were planning an observing session, you didn't quite know what to look at. Let's look at some double stars in a certain area, say between RA 3 hours and RA 5 hours, and between the equator and 20 degrees north declination. And we want the primary star to be no fainter than 9th magnitude, and we want the separation to be no closer than 2 arc seconds. You can put all those parameters in there, and it crunches out a list for you. And then you can go and observe it. So it takes some doing. It's a bit of a learning curve, and I could run people through that as a workshop at some other time. But it's an absolutely amazing resource to make observing lists and to look up information. It has all the latest information from the Washington Double Star Catalog, but in a much more easy, to digest format. And I recommend Cloudy Nights Forums, of which I am a member. It's free. It's very, very well moderated. So there's no loony bin stuff happening on it. You get kicked off there in a hurry. And they have a double star for them. So there is that. 3 books, certainly 2 books that you should have. The Cambridge Double Star Atlas is a wonderful atlas, and many of you will have a Cambridge Atlas. It's basically this, but it's not the Double Star Atlas. The maps for the Cambridge Double Star Atlas are at the same scale and the same look as the other book, as the other atlas, but it's got lots of double stars in it, and 20 pages of text at the beginning, basically talking about what I've already talked about. And then there a in-depth book, also by James Mullaney, double and multiple stars and how to observe them. And it has some good lists in it. The trouble with double star lists is, especially if they're moving, they're close, they become rapidly out of date. They come out of date. Some of the wider pairs like Albireo, that probably looked the same for 200 years, or Mizar and Alcor and stuff like that. But some of the tighter stuff, the more interesting stuff, it's moving, and so tables will be out of date. And if you want to get into a little bit more of the science of it, Robert Argyle, who was president of the Webb Society of Observers in England, with a specialty in double star, an extremely detailed book about the observing and getting into the science of measuring visual pairs. I have a talk on that. Mary Lou's seen it. That's the one I gave at NEAF about 5 or 6 years ago. Mary Lou? Can't remember.
Yeah,
Do you recall that?
I think 5 years.
Yeah, so and there's lots of other, and there's no shortage of places to get observing lists. The Astronomical League has lists. Any star atlas will have some lists, or they'll have them indicated. But one thing you can do is take an atlas like Uranometria or some atlas and just poke around and look at the double stars without knowing what you're going to see ahead of time. You just see some stars identified as double, get your scope on it and see what you can see. Write down what you see, then look it up and see how accurate your observing skills are. That's a whole other project. So there we are, and there I'll be in February. So any questions about anything else?
That your
This is
teacher?
excellent, thank you.
So no questions then.
Is that your scope that Teeter made for you?
That's a teeter, yes, sir. I don't have it anymore. I've gone small now because of arthritic problems.
Yeah.
I'm having trouble lifting things and grasping things and so on. My guitar playing career is almost over. It's pretty sad, osteoarthritis, because you can't reverse osteoarthritis. So we'll see what the future brings. I'm running an 8-inch Celestron, which is nice and light. It's only 11 pounds on a little Altaz mount, motorized go-to. So it's pretty good equipment, and it'll do me, and I can lift it all. But this big beast, no, not anymore.
Oh, geez.
I know.
Anybody?
It's the circle of life. So there you go. I'm going to stop sharing at this point. Oh, I have to do this. Here, stop share. Okay. Thank you for all staying all the way to the end. I know it's probably you're going to need a washroom break.
Need some medicine?
Oh, just a minute. Oh, I got medicine. Look, I'm still working on this glass. I've just been sipping away at it.